Good day, all. This is Oliver White coming to you live from beautiful Prague, Czech Republic. With me today is Dr. Roland Kuhn, author, speaker, physicist, and the team lead for Akka at TypeSafe. While I introduce Roland, I'll pop up a quick poll that asks you about your project or organization and what's kind of driving them towards this concept of reactive. So I'll leave that up for a minute. Here we go. Perhaps some of you have noticed that Roland and his telltale Homburg hat have not been making so many public appearances of late. Well, that's because Roland went into self-imposed exile for some time in order to put his full efforts into the book from which this webinar takes its name, Reactive Design Patterns. By the way, Roland has a 39% discount code for the book in the beginning of the presentation. Final things. If you have any questions, please place them in the questions tab of the GoToWebinar control panel, or you can email me personally at oliver@typesafe.com. As always, a big shout out goes to our happy customers, but especially one customer, HBC Digital, who is looking for a talented developer with Java, Scala, Akka, and Play experience to join them in Manhattan, New York. And that's a pretty interesting location to be sure. All right, let's close the poll. Now, without further ado, let's hand it over to Roland. Welcome, Roland.
Thank you, Oliver. It's great to have this chance of presenting this this talk. So, as Oliver already said, this is about reactive design patterns, which is the title of the book. And now, before anyone of you is disappointed, this is just casting a few spotlights into the topics that are covered in the book. It would be completely impossible to describe all the things that are in there in 1 hour. So here's the promised slide with the discount code. So it's currently published in the Manning Early Access Program with all 17 chapters, at least in a draft version. You can get 39% off with 39 KUHN. What is outstanding right now are the revisions and then the copy editing and so on. So I hope that it will be published in summer at some point. So this year, just to be clear. Now, let's dive in. So we begin with the question of what is this reactive thing? Isn't it just a huge hype or buzz? What is it all about? And for us at TypeSafe, and for me especially, it's not at all a hype. It has some very basic meaning that is interesting to many people who write applications, especially those that run the internet. Sorry. Is some sort of mix up. Yeah, now the thing happened with this panel that I cannot close it. Yeah, okay. Sorry for that one. I'll need to figure out how to switch slides because GoToWebinar displays the control panel in front of everything. Anyway.
Roland, you're a programmer and an architect and physicist. I don't expect you to be able to use slides. Okay, just for the record.
Anyway, I was saying that so when you write an application and you offer it to a potentially large audience, you're doing so in hope of being successful with it. And this means that you need to design the application such that it can actually live up to this expectation. Say you have a brilliant idea and you create an app that is consumed by a few people who then tell you that this is good, this is great, refine it a bit, and then it gets discovered, and then someone posts some big articles about it, and then lots of people come and want to use this product, and the site just crumbles under the load. That wouldn't be good, because just at the point where you were about to be successful, the whole thing failed, and nobody will even remember your name. Or the name of your carefully chosen application. What you need to do in order to prevent this scenario from happening is to consider elasticity as one of the core tenets, one of the core design goals in your whole application architecture. This means that you need to write the software such that you can make use of more than one machine if you need to, because it is quite obvious that if you have one computer to process all the things that you want to do, this computer is limited. It has limited main memory, it has limited CPU cycles per second, and this all translates into a limited, a bounded number of users that it can support for your application at any given time. So if you want to grow beyond that number, you need the ability to process requests on more than one machine, and that leads you into often the cloud. A computing center is therefore on this slide showing that computing power is at our tips. We can use it readily by using Amazon EC2 or Google Compute Engine or any other cloud provider. But in order to profit from these infrastructures, we need to foresee that in our application design from day one. This means that we need to write our application such that the incoming load can actually be partitioned. We need to make sure that the incoming load consists of pieces that we can route to a large number of processing entities, to a large number of computers that then compute the responses that need to be given. And this means that we need to consider this partitionable property of the load that the application experiences from the outset. What we want to achieve is that we can distribute the load that our application sees over multiple nodes. And this way we have basically no limit anymore in how far the application can grow. There is another aspect here that also leads us to distribution, and it's a quite simple one. If you have ever tried running a computer system, you will have noticed that sooner or later it fails. There are many reasons why failures exist. First, we make programming errors, of course, but there are others that are even more inevitable, and that is that hardware will fail. Computers will fail due to power supply outages, disks will fail, networks will fail. It is also the case that humans frequently make errors. For example, if you have a RAID 5 array for storing data on disks, and there is a faulty drive, and then someone comes in, has a bad day, replaces the wrong hard drive, all data are lost. So mistakes happen, failures happen, that's just a reality. There's only exactly one way to protect your system from failure, such that even when failures happen, it can continue to function, and that is to not put all eggs in one basket. This means, or says nothing else than that the program needs to be distributable. It needs to be distributed across different computers, in different locations preferably, and it depends entirely on your paranoia level or requirements for the application, how far you need to distribute. It might be fine to just have it in the next room, it might need to be on a different network switch, or it might be that it needs to be in different countries or on different continents. It depends entirely on how resilient your program shall be, but the point is you need to distribute it in order to achieve this. Now, if you have written your program such that you can distribute it for elasticity and resilience, what you have achieved is, what the result is that the application stays responsive. It stays responsive under varying load. It can adapt to incoming load, and it will not be overloaded as long as it can actually add and use more resources. And it also stays responsive in the presence of failures. This means that any given component can fail, and since we have distributed, made copies of everything, made it fault tolerant, these failures affect only small parts, and the system as a whole keeps functioning. Responsiveness is what you usually need for any service that you offer on the internet, because if your website is down, then, well, business is taking a hit. That's quite obvious. But there are other benefits as well. The main one that we have achieved is that we have decoupled the internal parts of our application from each other, such that we can actually contain failures, such that we can avoid cascading failures across component boundaries. This is necessary in order to make resilience work. But it also means that the implementation details of these components cannot be that strongly coupled, because otherwise, how can the cascading failures be avoided? This means that the components all have a clear and well-defined responsibility. We know of this as the single responsibility principle that we will discuss further in the following. And it also means that we naturally arrive at an architecture where things tend to not be shared. It is very close to a shared nothing architecture, and if you look at what CPUs are designed for, how the internals of our computers look like, then less sharing means less contention, less coordination overhead. It means better scalability. And of course, all these are the central points why you want to develop your system in microservices. You want to split it up into components that are, well, contained and decoupled. And this gives you flexibility in that you can add components more easily than in a monolithic design. But there are other benefits. If you have decoupled the responsibilities of the components that your system consists of, that means that you have a well-defined notion of this thing does, this component does one thing, and it does it in full, and this means that you can give this job, this task to one team, and different components can be easily developed in parallel by different teams. The decoupling is also visible not only at runtime and in the code base, but also in the organizational structure that develops the software. This means that you can have an easier time developing the pieces each at their own pace, and that you can have it can implement continuous delivery and all these nice things that we want to have nowadays in order to deliver an experience that is always up to date and can adapt quickly to business changes. One thing that you will encounter when you try to write systems that have all these nice benefits and that implement elasticity and resilience, you will find that you will concentrate on messages. Messages is a very old concept, as old as letters and any sort of postal service. Messages have the advantage of decoupling the sender and the recipient. It means that you can send a message without being encumbered by the time it takes for the message to travel to the recipient or whatever the recipient wants to do with the message. This decoupling is what allows you to achieve resilience, to contain failures and so on, because if only messages are exchanged between components, that makes it a lot harder for failures to spread, as it could easily, if the components were more interwoven, were using the same runtime threads and so on as it has been in the past. But this also has another aspect. So once you realize that you're mostly dealing with messages that are exchanged between components, focus shifts from class diagrams and interface definitions to the message flows, how the information flows within your system, the protocols that are applied between components, where protocol is not something like TCP or HTTP. That's not what I mean. A protocol is the structure of a conversation between two parties or more parties. It defines the exchange, who says what at which time. These protocols describe how the messages travel through the system at the highest level. Now, messages need to travel, and for that, they need to be transported. like letters are transported by the postal service, we need to deliver our messages within our systems. Currently, the lingua franca between microservices is HTTP. And I had on this slide written simply HTTP as a common network transport. But then I was told that most people assume when you say HTTP that it is blocking and synchronous, which is not at all true. So I mean an asynchronous HTTP way of handling HTTP, where you can send a request without having to block the thread to get the response. And then when the response comes back, you deal with it asynchronously by getting it into your actor or attaching a callback or what have you. This way, you can build RESTful services that are not devolving into RPC, but that actually implement decoupled components that speak higher level protocols. You can, of course, also use other things like message brokers, RabbitMQ, AMQP, all these things that are well established for delivering messages from one point of the system to another. And, well, I'm the Akka tech lead, so actors must be on this slide. Actors live and breathe messages. That's all they ever do. But it's not necessary to use actors. If strictly speaking, you need to view your system design such that you look at the message flows, and that has big advantages already. Now, if you pull these all together, we can arrive at this slide, which is a slightly different way of looking at the reactive manifesto. First, we have the values that we want to achieve. These are responsive systems that are maintainable and that are extensible and flexible. And the means by which we do that is that we design them for elasticity and resilience. And we note that the form of these systems takes great care to consider the messages and how they flow within the system, so this is why we call it message-driven. So this goes from high-level values down to implementation details, this diagram. This concludes my short introduction to reactive. Now, let's dive into the patterns. I will just show you 4 patterns in 2 groups. The first ones are architecture patterns. They do not really influence the code directly. They influence more the design of the whole system, how you go about it. They basically are applied on a whiteboard, if you will. The first pattern is the simple component pattern. And it says, a component shall do only one thing, but do it in full. Now, this is my formulation, but the pattern actually is very old. It is known as the single responsibility principle that was formulated by DeMarco already in 1979. We will see when we study reactive systems that none of these things, most of the implementations that we are looking at, most of the patterns are either very old, or by which I mean 30, 40 years, or they are inspired by old technologies that have already been discovered back then, but that are really starting to shine just now. DeMarco describes this pattern in the book with the first quote I give here. The aim is to maximize cohesion and to minimize coupling between components. This means that you put all the things that belong together tightly together, and you separate it from everything that does not belong to it. And another formulation by Uncle Bob Martin in the context of object-oriented design is that a class should only have one reason to change. That might be a well-known phrase as well. Now, what does this mean? Let's try to take a look at implementing this pattern. The example that I'm using here is that of a batch job service. A batch job service is something that you can, well, submit batch jobs to. So users submit jobs that are supposed to crunch some numbers, say, and that get some inputs from some file storage that you have, maybe, and that provide an output. maybe a report, maybe a single number, doesn't really matter. So users submit jobs with a higher level business purpose, but then there are many users. You have this service because you want to efficiently use your resources, so there needs to be some engine that does a lot of planning, that validates incoming jobs, that looks at user quotas, and makes sure that everyone gets their fair share of this system. Then the execution of these batch jobs shall be done on some elastic compute cluster so that the capacity of the system can be adapted to the demand at runtime. And last but not least, users want to be able to see what their jobs are doing, how they fare, whether they are completed or not, or what kind of results they computed. So this is basically what a batch job is. It is well known to me because that's how we used to do big data at CERN way before the term was coined. And that is basically how I got from physics PhD into programming. So, but let's look at how we would sketch this. We know already that there are probably two pieces that we should separate. We know that there is this execution that we need to organize, and that will have to manage a number of computers and send the batch jobs to them and collect the results and so on, and make sure that everything keeps running. So we would say this is a responsibility for sure that we need to split out. Now, on the left-hand side, we have all the clients, all the users that want to submit things. And between that and the execution, there needs to be a lot of coordination. Now, while it might be possible to describe what this execution thing does, such that a team might start implementing it, it's probably not a good idea to tell a team, you implement some coordination. That's too vague. That's not one single responsibility. That's too big. So we need to split this up. We need to make it smaller. And how would we do that? Well, there is one piece that we can foresee, and that is that the clients need something to talk to. They want to submit jobs, they want to query jobs, and for that, typically we would have, for example, a REST API that does that. On the other end, the execution engine only needs a list of batch jobs from which it pulls and executes the next one, and these two are not really related. If one goes down, the other does not need to go down, because if users can't query anymore, that doesn't mean that the execution needs to halt. So we might want to keep those separate. And then there is the concern that once a user has submitted a batch job, and they got the okay that it was in queue, they really want that job to run. It wouldn't do that, we just don't do it. So there needs to be some sort of storage facility that keeps track of what was submitted, so that after a system crash, for example, if the whole computing center goes out of power, everything shuts down, and when it comes back up, it shall restart running the jobs, right? So it might look a bit like this. This coordination part will be split up into the client interface, into the storage implementation, and the job scheduling part. And these lines are just simple relationships, like who talks with whom, but they are not very specific in this picture. The point that I'm trying to make is the simple component pattern is about finding responsibilities and defining them clearly, such that if you have something that needs to be done in the system, you should be able to determine exactly in which of these boxes it should go, which of these components does a certain thing. And that is described by its responsibility. And the other part is that this pattern is best applied in a recursive fashion, because you typically start with a vague and high level and big idea of what the system is that you're building, and then you drill down more and more as you design things, as you flesh out the system, and then you discover more and more components that you might want to define until you start working on them. Of course, the simple component pattern is named simple and not trivial component pattern. So this is not about the code size or any of these measures. It's really about having a responsibility. And if you break things down recursively and you really get into the mood and keep doing it, keep doing that ad infinitum, that means that the resulting components that you design will be too small. They will not really have a responsibility anymore. They will be trivial things that have no reason to exist. So caution, apply it recursively, but make sure that you stop when you see that you can't split things anymore, while still retaining the notion that there must be a real responsibility in each of these. So this is about the simple component pattern. There is another pattern. Yeah, I think I skipped over that one. Sorry. There is another pattern that I would want to talk about, and that is the let it crash pattern. I paraphrased it as prefer a full component restart to complex internal failure handling. Now, what does this mean? This sounds a bit odd at first. So this is also not new. As I said, most of the things are not new. This was published by Candea and Fox in 2003 with the title Crash-Only Software. The point here is that there are failure conditions for your systems that you will run into once in a blue moon. And these failure conditions might be really hard to debug and figure out. And it might be even more costly to really fix them and make sure that the fix is correct by writing a test, because it might be a rare race condition that you cannot really force to occur. And in those cases, so where you have done all the reasonable fixes already, and you just have these rare things remaining, then they say it is much better to rely on restarts than to try and handle these failures as well. There is basically a point beyond which it doesn't pay to handle failures in a specific fashion. A full component restart means that you completely set it back to a zero state, to a known good and working state. For example, if you have a worker node in this batch job service, you can just deprovision it, tell EC2 to scrap it and create a new one from an image that you know to work, and then this node can be taken into service again. This would be a full restart. A restart's goal is to wipe all the state that the component has accumulated and that could be responsible for this failure condition. This means that for these failures, you really take a very simple failure model. Either the component has experienced such a failure and then it will be crashed and restarted, or it hasn't. That's a pretty simple one. Compare that to that you measure all sorts of things, you catch exceptions, you keep statistics, and then you try to figure out, oh, this looks fishy, now I might want to do that. No, that's a much more complicated failure model that is also easier to get wrong. This is the big benefit of this pattern, that it makes the handling of failures possible that you did not foresee, and that it does so in the simplest possible fashion. This pattern has been in the Erlang philosophy from day one. We always quote this reliability number from the switch that they produced in the middle of the 90s, which has an uptime of 9 nines, which is legendary, and that is attributed, I mean, if you want to write such a system, you want to build such a system, everything needs to be really reliable, because every component that you add, hardware or software, can only make it less reliable. And for the software part, this pattern is attributed as the source of the success. Actors are very convenient for this purpose because actors completely encapsulate and shield whatever they have inside. And if they experience a failure, you can just remove the actor and create a new one instead. That is in Erlang, and that is, of course, also the central piece of what Akka does. On another scale, this let it crash pattern has been popularized by Netflix, by the Chaos Monkey and the Simian Army that they use to make sure that their system is working. Netflix, of course, needs a huge server farm, and when they grew explosively, I would say, exponentially, in the beginning they had no good measures in place to make sure that the system can deal with all sorts of outages. Any single host can fail, and if you run 100,000 of them or several 100,000, then of course chances are that something is failing at all times. Now, instead of just waiting until that happened and then worrying when it does, they installed a system that applies the let it crash pattern in the other way around. So instead of restarting a component which was faulty, we ensure that we have the capability of always restarting, no matter what the reason, by just inducing these restarts randomly. And that's what the Chaos Monkey does. It kills parts of the system continuously on the running system to make sure that all countermeasures are working properly. And of course, well, normally you would say, let's do that on a test system, on a staging system that we run on the side, but there is no second planet on which you could deploy a second Netflix, so that's not an option, and that's why all this is done on the real system. The takeaway here is failure will happen. It's not something that you can avoid. Fault avoidance is ultimately doomed. The only thing you can do is to embrace failure, assuming that it will happen, and install the countermeasures that deal gracefully with it. And this is the essence of the let it crash pattern. So let's come to the second part of the patterns, and that is about implementations. Implementation patterns are more related to code and how you structure at a smaller scale. The first one that we'll talk about is a well-known one. It's called the circuit breaker pattern. Protect services by breaking the connection during failure periods. Well, we know failure does happen, so we need to do something when it happens. And a circuit breaker is a well-known thing. The concept is very much inspired by electrical engineering, where the idea is that you have a consumer electrical circuit that is connected to some other electrical circuit to draw its power from, and what you put in between the two is a circuit breaker to make sure that if that other circuit misbehaves, so it draws too much power, then that failure does not bring down the whole system, but only that part which was experiencing the short, for example. This is not exactly how it works in computers, because we don't really measure currents and trigger on overcurrent. We trigger on failures instead. But the picture I have in mind still very much fits. This was first published by Michael Nygaard in Release It, later also blogged by Martin Fowler and others, and is a quite popular and central pattern, which basically protects both sides of where you apply it. You have a client that makes calls to a service, so you put a circuit breaker in between the two, and that allows the client to react to repeated failures by concluding that the service is currently unavailable. What happens is you have a circuit breaker implementation that monitors the service calls and the results that they give, and when you have a number of failures, like 5 in a row, then the circuit breaker opens and no further requests will be made. Instead, a negative, a failure reply will be generated locally at the client. We don't need to wait for the signal to travel to the service and back as a request and response pair, or even if there is no response due to overload, we don't need to wait for a timeout. We can conclude immediately that we are not even trying because the circuit breaker is open. And then after a certain time, the circuit breaker goes back into a half-closed state where it will permit some requests through, and if they are successful, then it's closed, everything is good again, and the world is okay. But otherwise, if it's not yet okay, then it will just snap back open and continue to protect the client. But this also protects the service that you're calling, because if the failure was, or if the problem on the service was due to overload, then the circuit breakers being open means that the service can have some breathing room to empty its queues or whatever it was that it was experiencing and get back to a normal behavior. So a circuit breaker protects both ways. Here's some code that shows you a circuit breaker example based on Akka. Circuit breakers are quite frequently available in several frameworks, so Akka has one as well. Let's imagine that we have a method called send to storage, which returns a future of storage status. Now we can protect this, which makes a call to the storage system, let's say from the client interface in this batch job service that we have implemented, right? So we have this circuit breaker that we configure. It needs a certain scheduler for scheduling timeouts, and then it is configured with a certain number of failures that trigger it, and it is configured with an interval after which to try again. And the circuit breaker implementation in Akka also triggers on when calls take too long. So it does not install a timeout on the future itself, but it notes when the futures are completed after a too long time. And then if that happens, that's counted as a failure. And then the circuit breaker will open if that happens repeatedly. Now the only thing you need to do is to wrap the call to send to storage, as shown in the lower part of the slide, in with circuit breaker. And that will just run this code such that the creation of the future, the method call to send to storage, is taken as a function argument. This is a by name argument in Scala, which means that when the circuit breaker is open, this call send to storage is not even executed. Otherwise, if it is closed, it is executed, and the future that it returns gets another callback installed, so the circuit breaker can monitor things. And then, depending on what the result was, we get back either a storage failed, a timeout exception, or if the circuit breaker was open and did not actually make a call to the service, we get a circuit breaker open exception. There are other implementations, but this is kind of the typical, the gist of it. So then we have another pattern that's called the Saga pattern. This is one that many people ask about when we talk about microservices, and we'll see why in a second. It says, divide long-lived distributed transactions into quick local ones with compensating actions for recovery. This is a bit complicated, but the reason is that what this is trying to solve is also not an easy problem. For the background, consider that we have done a microservice architecture. This means that we have distributed the knowledge of our application across many microservices, where each one has its own responsibility and each one also owns its data. There is no more central database that you can query to get all the truth, because having the truth in one place is a scalability bottleneck, and that's precisely why you went with a microservices architecture. You can read up on the consequences and the motivations for that in some excellent papers by Pat Helland, like Life Beyond Distributed Transactions or Memories, Guesses, and Apologies. The thing that then usually pops up is, but what do I do if I have a business process? So I have a business transaction that affects multiple microservices. Normally, you would have used something like a distributed transaction, but, well, that doesn't really work in practice. The implementations are not as powerful as we would like, and performance is really not good if you use those. So what are we going to do instead in a microservice architecture? Well, turns out that someone has solved also this problem like 30 years ago. Garcia Molina and Salem have published a paper called Sagas, in all caps, in 1987. And this describes how to handle transactions that are long-lived in the database systems that were known at that time. At that time, databases were local. They were not spread across network nodes. Computers had just one CPU with one CPU core, but still there was this problem that the database would be holding locks on certain tables, for example, for each transaction. And if a transaction takes a really long time, like an hour, then all other transactions that need to touch the same data will be deferred by that 1 hour, and the database will seem really slow, even though it is not really that much at fault in this case. So the solution that that these two people propose is that we break up the long-lived transactions, and we can use the same principle to break up transactions that are touching multiple microservices. We'll take the prototypical example that's usually used, which is a money transfer between two accounts. Everybody knows that this is not how banks operate and that this example is fundamentally flawed, but let's just assume that we want to do it this way. So instead of locking both accounts, because both would be in different microservices in this example, just to make sure, right? Instead of locking both accounts, we split up this whole process into two transactions. First, we have one transaction that takes money out of the account X and puts it into a local working account. Local means no coordination, no contention necessary, because this is owned by the Saga. And then we have transaction 2, which transfers the money from the local working account into account Y. What we need here, because these are separate transactions, if transaction T2 rolls back, if it cannot be completed, then we need to make sure that the money reappears in account X, because otherwise it would be lost, it would be gone. And this is what the compensating action C1 does. It compensates for failures by transferring the money back into account X. So this means that the only thing we need to do is we execute T1, then we try to execute T2, and if that fails, we execute C1, otherwise we're done. There is one obvious thing to mention here, and that is that if another Saga were running concurrent with this proposed scheme, then it could actually see that the money is missing in account X, while it is also not yet in account Y. It would be in the local working account of this agent that performs the transfer. So if you were to write a system where you can get a report from the overall system how much money there is, then you would have to make this one aware of the local working accounts of these Saga agents, and that would fix the global invariance. The point is, while there are certain consistency guarantees that you cannot implement in this scheme, you can usually achieve all the things that you actually need by adapting your system a little bit. We can look at this a bit more in detail. This is discussed in the paper. So in general, you have transactions T1, T2, T3, and then you have compensating actions C3, C2, C1. And if you need to recover after having committed T3, then of course you need to run the compensating actions in reverse order. The other choice that you have is that you can recover forward by using save points. So if you have transaction T1 and that has completed, then you take a save point and then you apply T2. And if that fails, you can start back from the save point and try T2 again. The thing is, that's a question that normally comes up if this is not given as a webinar. What happens if something fails fatally, or if the compensating action fails? What what shall we do then? Because then the system is broken. Well, the authors note, and I think that is very correct, but also very brave as a statement, that not everything can be fixed by computers. We cannot foresee every eventuality. Sometimes we just need to alert an operator and say, something has gone wrong here. Please look into the records and fix it manually. And the thing is that society has a system for dealing with those. So if you got more money out of the ATM than your account had, then of course the money will be reclaimed by the processes that are defined, if necessary, by suing you. So not everything needs to be done by computers. So just to show you that this is not something that is highly theoretical, I have implemented this bank transfer in Akka. So let's first define some interfaces. So the account has withdraw and deposit methods that return futures, and then we have the messages that we need in order to define what this actor will do. We have the transfer that defines the amount that is to be transferred from account X to Y, and then we have certain events that can have occurred. So when we start the Saga, we send this transfer command, and then the first event is, well, the transfer has started. We want to transfer amount from X to Y. And then we do the first one, then the money would be withdrawn, and then we do the second one, money deposited. And if we had to compensate, there's rolled back. So how do we write the actor that does that in a reliable fashion? This is an implementation of such an actor. It's the transfer Saga, so it's responsible for performing this transfer, and this Saga needs to have an ID. It needs to know its identity in order to be able to resume. Because if the machine crashes during any of this processing, the Saga wants to return back to the last saved state and continue running from there. So it needs to have its ID. Then the initial behavior is defined in the receive command. If we get the transfer message, we persist that we want to start a transfer. So the transfer is started is the event that we send to the journal, and once this event has been committed to disk and is available for later replay, then we actually start withdrawing the money. We call the withdraw method on account X in the withdraw money implementation. And then we map the result of the future, if it was successful, to money withdrawn. Otherwise, it would be a status failure, as you may know. And then we send it to the actor using the pipe 2 pattern. After that, we suspend the actor. We suspend the Saga because now we need to wait for the confirmation that the money has been withdrawn. And we install a behavior that can deal with this. Await money withdrawn is, again, a method that gives us a receive, gives us a behavior. And when we get the money withdrawn, then we persist that this has happened. So we persist the money withdrawn object, and we do the deposit money step. The deposit money step works exactly like the withdraw money step. So we call the deposit method, map the future into money deposited, pipe to self, and suspend the actor once again, awaiting the money deposited. Once we get that back, we can handle several failures, several states here. The successful one would be money deposited, in which case we persist that and stop the Saga because it has been completed, has fulfilled its purpose. But if it is a failure, we actually execute the compensating action and transfer the result of the deposit back into account X as a rolled back event that we then await. And once we receive that, we stop the actor again because now the Saga has completed, albeit with a negative outcome. So this is the operative, this is the normal behavior. the last thing that we need to look at is what happens if at any point in time the thing crashes, the machine crashes and is started back up again. In that case, all previously persisted events of this persistent actor will be sent to the receive recover behavior. That's the only function of this behavior. It will get all the events and then it will get a recovery completed message. So for the transfer started, we note that was the one that we that defines all the parameters, so we keep track of that, and then we just keep track of the last event that has been seen, and once the recovery is completed, we match on the last event and act according to the last reached state. If there was nothing, then we still are waiting for the initial message. If we have only started the transfer, we do the following step with this, which is to withdraw money, and so on. And if we see that the Saga had already completed by money deposited or rolled back, we can just stop the actor. So this is an example implementation. It doesn't handle all the corner cases, but it's the general idea of how to apply the Saga pattern. One thing I find quite interesting is that this is going kind of full circle with what we discovered or what we described in the Reactive Manifesto, and when we talk about reactive architectures, in that in this paper from 30 years ago, they note that we should search for natural divisions of the work being performed, which is the microservices splitting the simple components. Then it is the database itself that is naturally partitioned into relatively independent components. That again is fully compatible with the view that each microservice, so each partition of the function, also owns its partition of the data independently and exclusively. The database in the Saga should be designed so that data passed from one sub-transaction to the next via local storage is minimized. And this means a share-nothing architecture. This means just passing messages that inform the next steps, but not passing the private data that you need, that you mutate. So this is all of this is fully compatible and fully aligned with the concepts of simple components and isolation, aka microservices. This brings me to my conclusion, namely that reactive systems are, in their very nature, distributed systems. And this requires some new, well, we discover most of them old, architecture patterns, and it is also helped by some new or old code patterns and abstractions that we see being made good use of, and that we see coming to new use right now. But there's one thing that you should always note, and I mean, you know, distributed systems are hard, and applying these patterns does not make them easy. Thinking is strictly required. And that is all I would like to say on the topic. Thank you.
All right. Thank you so much, Roland. That was a great presentation. I was learning something myself, which is wonderful. We do have a few questions. We have a few minutes for those. I think touching on something that you were more recently discussing in the presentation, what is a good recovery strategy to restore normal to get normal operations back after a circuit breaks? And are there any built-in alert mechanisms or recovery mechanisms to handle that?
That is a very good question, because one might be tempted to just, while the circuit breaker is open, so while your monitoring tells you that a certain service that you want to use is unavailable, that you just queue things, and when it comes back online, you send all that queue because you hope that now it will work. This is not a good idea. It will cause what is called the thundering herd problem, because usually there are multiple clients to a service, and if everyone does that and the service was overloaded before, then it will, of course, again be overloaded by all those queued up requests that now come in quick succession. And even if it wasn't overloaded before, then this thundering herd might actually make it so. And then the system would oscillate between circuit breaker open and closed, and nothing would really work. So you should use the knowledge that these circuit breakers or other monitoring tools gives you in order to deliver responses to clients that say, something is not working quite right now. I might have degraded service that I offer. I might not be able to give you the last detail of the operation that you wanted to complete. Or I might just give a failure response. And this is the proper thing to do.
All right. The next question, let's see. How do we prevent making our applications too dependent on a messaging structure? Does relying on messages make changes in message patterns and structures difficult since you are required to change the implementation in at least 2 services? That's pretty much verbatim. I'm not sure if it's clear.
Yeah, I think I see what it's getting at. Of course, you have the protocol that you have installed between 2 components. That is something that each of the implementations intimately depends on. If you change that, then you will have to make changes on both sides. This is a good and a bad thing. The good thing is that we talked about these components should not be trivial. They should have a purpose and a responsibility, and you should sit down before you start designing this, before you start implementing the system, to make sure that these interactions are good, that they all make sense, and that they exchange the data that absolutely must be exchanged. And you do that without considering the implementation, really, of these components very much. And the interfaces that you arrive at using this will usually be better decoupled, will be less coupled than if you were to design your interfaces just like Java interface classes, where it's so easy to just add another method. This means that messaging systems make this aspect of coupling or decoupling obvious. They make it front and center and make you consider it from day one. And this is the advantage that you get.
Okay. Thank you. Here's a good one for you. Are Saga patterns just another SPOF, single point of failure? Suppose your Saga is a separate service, a staging area for parts of transactions, and then that service itself fails. Does that make sense?
Well, you can, of course, so if you make the sagas themselves things that can be resumed, that are persistent and so on, as I have shown, then if something goes wrong, you can just spawn up a new copy of that system that runs these sagas. So they are very much amenable to all sorts of resilience patterns of replication and starting multiple executors for them. The other thing is that sagas factor out the business process, the behavior that crosses multiple components into one single place, and that is desirable for other reasons as well, because these sagas are something that you can simply sit down with your business folks as a programmer and talk a common language of what they do, because the components that they speak with and the interactions that they have should have business meaning. And then you can simply discuss, okay, this does that in that order and so on, which is quite some value right there by having it factored out into its own component, instead of having it intertwined with all the other code that just happens to be necessary for running all the different microservices that participate in such an action.
Okay, and one last one. In terms of reactive streams and the transport protocols used there, is it possible to start designing systems without using REST APIs or having to define those in advance?
One very good way of doing that is, of course, by prototyping the system using actors, because actors are message driven from day one, and you can run them, of course, all locally in the same JVM. You can have the whole system happily running inside your IDE, for example, for writing it, and then you can distribute these actors because they only define behavior, not the messaging relationship that tightly. You can just distribute them across a cluster. You can distribute them across different services that you then later couple using different protocols. So you could have an actor making a request to an actor, another one replaced later by a REST call, for example, and the route that receives the REST call will transfer it back into an actor message that then gets sent. So I would say, starting from that one, using actors is the perfect model, because actors express exactly what it means to be distributed.
Great. Well, thank you very much for joining us today, Roland. To all the attendees out there, thank you for joining us as well. If you want to learn more, I guess the best place to go is Roland's book. I've put a link to that in the chat window. And you can also go to manning.com and type in reactive design patterns to find it there. So again, thanks everybody, and we'll catch you next time. Have a wonderful day.
Thank you, Oliver.
Thank you, Roland. Bye-bye.